already start introducing Bo. So it's a pleasure, and that we will have, so Bo Sundborg, we will speak about thermal large-N holography. So you are welcome.
Okay, thank you. Yeah, my sound is on, yeah, okay. Yeah, I'm very grateful for the organizers of this nice workshop to be able to give me the opportunity to talk about thermal large-N holography, which is my favorite topic. In particular, I'll talk about extracting information about somewhat complicated features of the bulk, tidal excitation for motion around a compact object, to extract that from thermal mixing in the boundary. This is work in progress with my PhD student Julius Engelsøy, and let's see. Yes, so you might wonder why I like to talk about thermodynamics and thermal properties in a workshop that is focused on mainly on fundamental and formal properties of gravity, strings, and higher spin theory and integrability. For me, the motivation is clear. Gravity gives us definite signs that space-time is like Bekenstein-Hawking entropy, etc. It's sort of intimately connected with thermodynamics. So the idea is to try to explore that and do that in quite unusual settings, not Einstein gravity, but these exotic, very stringy and higher spin symmetric versions of gravity. You could ask then if these theories, in these theories, is physics still recognizable as gravity? Are there important universal features, universal lessons to be learned from this connection to thermal properties and to large N, which is essential in sort of top-down versions of holography? Still, we would like to test these ideas on practical examples. How does gravity behave? And there's an interesting notion of what's called bulk cone singularities that I think was introduced by Hubini, Liu, and Rangamani quite a few years ago by now. And I want to start from this image that I cut and pasted from their preprint because it's actually relevant to the calculation I'm going to explain later on here in this talk. So what is this? The black circle is the boundary. This is a view of space. Left-hand part of the figure is space. Boundary of ADS or asymptotically ADS is the black circle. The right-hand side is the corresponding time evolution. So you have a light signal that is sent out from the point on the boundary, and then you see it how it evolves with time. Sorry, from here. That's the origin. Evolves with time, and this is through space. And here you can see the presence, in this case, of a perturbation in the center of ADS, which happens to be a star. And geodesics, light geodesics will be deflected. If you image this on the cylinder and plot where the light rays end up, you get the below picture from a much more recent paper by Dolson and Oguri for a similar situation. This is a black hole rather than the star. And you will see this line of sort of painted by the light rays on the boundary, which is slanted compared to the actual light cone on the boundary. So this fact that you get images on the boundary from that are modified because of the presence of a compact object in the center is what's interesting. And you could ask if this can be reflected. Can we see this in a fundamental model in these very exotic versions of gravity? That would be the ultimate test of seeing compact objects, right? Douglas and Oguri, they are able to connect this story to tidal excitations. If you send strings rather than point particles into the bulk, the strings will be tidally excited when they pass inside the photon sphere around the black hole. So we're also interested to see if we can detect that in these simple models of holography. So that's the aim of this work. Now, I want to mention these recent developments that I think are related to this story. Of course, the nice work by Matthias and Rajesh on duals of free super Young-Mills work that Matthias presented is very much relevant to the kind of model we're interested in studying, although our models here are just toy models, much simpler. This kind of model has been used also to extract properties of the geometries by Eberhardt earlier this year. This set of references centered around Olsen and Oguri, they discuss this kind of use of thermal field theory in order to thermal CFT in order to extract information on the bulk or the reflection, how things are related between bulk and boundary. Now, to understand this better, we need properties of thermal CFTs. And, I'm sort of in between two talks here by Matthias Gabidil and Sergei Parnachev, and it connects to both, which is nice for me. And in particular, in this paper, Parnachev et al. Describe very interesting phenomena by themselves, but also review some of the recent interest in thermal CFTs. And that's interesting for fundamental reasons. For instance, that there are limits to the convergence of the operator product expansion due to topology, that the fact you have a compact thermal circle limits the convergence rate. And there are new simple but non-trivial observables, like one-point functions that are non-zero, and that different operators or operators of different conformal dimensions will mix, essentially because you sort of break conformal invariance softly and you introduce a scale. All right, this whole story of trying to extract bulk physics from boundary physics rather than the reverse was inspired by Witten's observation very, very early on in the holography story that Hawking-Page black hole thermodynamics will reflect itself in deconfinement phase transitions in the boundary large N theory. In free super Young-Mills, you could go the other way from the boundary and check the thermodynamics and find that there is a thermodynamic phase transition in higher spins symmetric tensionless string theory. Whether that's a black hole or something else is of course not really clear, but the characteristic of the phase transitions, the fact that there is one, is very much reminiscent of the Hawking-Page story. Now, to better analyze this, you need to probe what the space-time is. And how do you do that in holography? Well, you calculate boundary correlators, and this story we have developed in recent years, and the picture is more and more clear that these objects, whatever they are similar in many ways to black holes. So for the purposes of this talk, I will call them black holes, although we don't have concepts like horizons. And actual black holes, of course, will not have horizons because they radiate. But, you know, in some way, this physics should be reflected. One way that physics can be reflected of very strong gravity is that composite extended objects should be tidally excited. And this is the purpose of this study, investigating both tidal excitations from thermal mixing in the boundary. Now we want to approach this whole issue technically. How do we do that? Well, we have to encode the background geometry, and background geometry in thermal equilibrium is believed to be a black hole or something similar. Global ADS is topologically as a sphere times r, the time direction. And if we want to do thermal equilibrium physics, we make this a sphere times the circle, where the circumference of the circle is the inverse temperature. So we are supposed then to study path integrals like this, where we have a number of fundamental fields that describe our large N theory. Here, these fields are scalars, but they have something in common with the sort of title of this conference, Quartz 2020, because they are in our example scalars, but they transform into the vector, the fundamental and the anti-fundamental representation of S of UN. So they're like quarks and antiquarks, although scalar versions of them. Now, mesons are obtained if you take a quark and an antiquark, and similarly we get invariant singlets in this model if we take a fundamental scalar and an anti-fundamental scalar. So we call these kind of models singlet models, and they include higher spin theory, boundary descriptions of higher spin theory, and of tensionless string theory. Although here we will focus on the very simplest examples, and work actually in unphysical dimensions, not the standard dimensions, but in dimension 4 in the boundary, which for vector or fundamental anti-fundamental representations would represent ADS 5 rather than ADS 4, so it's a bit non-canonical, so to speak. Now, in any case, mesons, the singlet states are should be the physical states of this model, and they are represented by these combinations: anti-fundamental and fundamental representations. This is the lightest operator, and then you can describe excited states, so to speak, by adding derivatives in certain ways, like this. You get a spin 2 current that is conserved like the other currents when you have free field actions. So this is the set of higher spin currents that are conserved because of the free equations of motion. That's the boundary equivalent to the higher spin fields. Let's see. Yeah, that's what I wanted to say here. So among others, you have the graviton corresponding to the stress tensor in the boundary. All right. But we need to represent gauge invariance somehow under the Singlet condition. So how do we do that? Well, in the path integral, we introduce a gauge field, even though eventually we're going to decouple it, because we're taking the free limit of super Yang-Mills theory, if you like, that Matthias talked about in his talk. Now, we have to be careful, though, when we are working on at finite temperature, because space is, or space-time, the Euclidean space-time is not topologically trivial. So there can be gauge fields that are non-trivial along the S1 direction, and that means that it doesn't completely decouple. These fields don't completely decouple even in the gauge coupling to zero limit. So they will remain and they will produce the Gauss law singlet constraint, which is the only remnant of gauge symmetry. But it is important. So we replace derivatives with covariant derivatives, gauge covariant derivatives, and then you have to include this integral. Now, next step is to be serious about the large N story. How can we take the large N limit and make use of that to get out interesting results? Well, the integral over the time component of the vector potential should somehow be an invariant integral, and the only invariant information A0 is its value, is eigenvalues. So that's what this integral reduces to. It reduces to an integral over n eigenvalues, where n is large. And the action can then be written in terms of an effective action for eigenvalues. The effective action depends on the temperature, which is just the radius of the compact time dimension. So finding a large N saddle point is the dynamical principle. And 1 over N is Newton's constant. So then, given the prominence of large N arguments in holography, when we do this saddle point analysis, we can expect to reproduce significant aspects of bulk gravity. All right, so what do we get? We get saddle point densities, the critical ones, solving this equation. These densities will vary with temperature, and qualitative changes in the equilibrium density of eigenvalues leads to phase transition. Here we have been forced by, time constraints and complications in the calculation to, at the moment, only study the extreme high temperature limit. And this corresponds to eigenvalue densities, whether it's the matrix model or the vector model that we're talking about right now. The eigenvalue density will localize to a delta function around zero, at zero. So with this information, we can go on to calculate correlators that probe the thermal physics at equilibrium. Note then that scale dependence of correlators, as always in holography, probe the radial direction in the bulk. All right, so we're ready to do some calculation. Momentum space 2-point functions and singlet scalars can be obtained through the constituents scalar quark, so to speak. So we have one constituent propagating along a standard free propagator, and another one in the other antiparticle representation propagating from and to the same points as, and that is how we sew together a propagator for the singlets, the singlet scalar fields, like this. We sew together two fundamental propagators and obtain a result. The result is this one, and the scale is set by beta, the inverse temperature. All right, we need two operators to compute mixing. The other operator, the next operator to study is the graviton. And in particular, we can take the 0,0 component of the graviton that measures fluctuations in the radius of Euclidean compact time direction. So this field is sort of analogous to the radion scalar perturbing circumferences in compactified spacetimes. It perturbs compact imaginary time circumference, which is related to temperature. And I will call this operator T. Here it is. And then we can study the 2-point functions. Singlet scalars. For singlet scalars, I displayed this, I calculate this correlator before. It is, as you can see here, it is given by a sum over eigenvalue contributions. In the extreme high temperature limit, as I mentioned, this distribution is focused to lambda equals 0, and it's very easy actually to calculate it like this. It's much simpler. We can also focus on short distances because the characteristic scale in distance goes to 0. Now, the point was to calculate mixed correlators, and they can be obtained in this limit by a trick, which is essentially applying sort of a point-splitted derivatives on one of the operators in an expectation value to get the correlator of here the T operator and the ground state scalar operator. So this correlator contains all leading information about thermal equilibrium. So it's really the main object. We can simplify even more to extract useful information. What we do is we look at static thermal correlators, representing how static perturbations respond to the presence of thermal equilibrium, which is sort of black holes. So consider these time-integrated versions of the correlators, like this, which can also be computed reasonably easily. It's a bit more complicated when we have the mixed correlator, but it's there. And now we can start extracting information from this correlator. As I emphasized repeatedly, the characteristic scale is again beta. To illustrate it, it's convenient to Fourier transform to momentum space, and the Green's function, the correlator at the static one, is encoded in a function f. That function f is given in this graph in a log plot. So we can extract all information from that plot. The mixed correlator then is constant for small momenta, and it falls as an inverse power law for large momenta compared to the characteristic scale, of course. So why is this, why do I claim that this is tidal excitation? Well, if we think about the bulk picture again, we would have, you can look at the case where we start out with the one field being sent in from the boundary of this asymptotically ADS space, which is the circle again, like in the image I showed you in the beginning. You send in the ground state operator from a position out at infinity. Now, I call that send in. We have the static correlators here, but there will be similar effects in dynamic ones. So a perturbation out here of the ground state scalar will actually lead to a response in a detection by an excited state static source at some other point in the boundary. But due to this fall off here in the graph, this effect will be zero if they are close to one another. That is, for high momenta, you have a small effect of this kind of conversion from the ground state to the excited state, or the higher dimension operator. However, if you're far enough for low enough momenta, if you're far enough away from each other, then you will see this correlation. You will see a transmutation or conversion of the ground state field to a graviton. And this mixing grows with temperature. But most importantly, this constant mixing of temperature and scalar fluctuations, they happen in the deep interior. So there's something drastic that happens at some radius in the interior. And of course, we believe that this is related to maybe not the horizon, but probably the photon sphere of these black holes or whatever they are. So we can detect the presence of some black hole-like objects. So, I mean, just let me mention this, that this is a sort of standard thing that you can mix otherwise independent field. That mixing can be induced by non-trivial backgrounds. For instance, you can think of observing if there are axions in the real universe, you can detect conversion of electromagnetic of photons into axions in strong electromagnetic fields.
I'm sorry, just to let you know, you have about 2 minutes.
Oh, I see. Okay.
Well, let's make it 3.
But thank you.
Sorry, maybe I should have told you before.
No, it's fine. I'm almost there. I was slowing down because I thought I had infinite amounts of time, like 7 or something. I don't know what. Yeah, I know why now. Okay, I'll finish. So this mixing arises because the constituent fields that build the same constituent fields build up both operators. So this leads to relations between large N-theory operators, allowing for mixing. Now I'm actually at the conclusions and outlook. So I would say that mixing is induced. We'll confirm that. For extremely high temperature of the static effect is large, especially for low boundary momentum, that is corresponding to the deep bulk interior. Correlators that are consistent with are then consistent with the presence of a compact bulk object emulating a black hole, even in these toy models of high spin gravity and tensionless string theory. The gravity there in the center appears to be vital for mixing. And this mixing discloses relationship between different bulk fields. This is expected in string theory, and we now also see that in high spin theory. Now, for the outlook, we don't yet have the exact correlator expressions for all temperatures and separations, but they are underway. If these expressions can also be processed, it will actually yield us complete information of the leading scattering process by quantum black hole-like objects. And the tidal excitation of the incident composite field is likely to be substantial only in the presence of strong gravity. So I would say that would mean that mixing is an ideal probe of regions inside the photon sphere, around the horizon, and perhaps close to the resolved singularity of quantum black holes. So, thank you.
Thank you very much, Bo, for this nice talk. So indeed, we are essentially on time. Are there some questions? I see several. There is Andrei Arnachev and Matthias also, but first Andrei.
Can you hear me?
Yes, yes.
Yeah, thank you for a very nice talk, Bo. I was just wondering, so if I understand your picture, you are at basically in the tensionless string limit. So you are probing all these tidal excitations in the extreme limit in a way. And I was just wondering if you could see, like if you could go to the other limit, where gravity is the right description, so lambda is large, and then consider, say, corrections, and see how these tidal excitations appear, and somehow see how a picture interpolates between point-like string and this long string that you have.
Yeah, I mean, that's of course ultimately extremely interesting. I think that picture closer to the standard gravity picture is explored a little more in this paper by Dodalson and Oguri, and in the intermediate case they get the PP wave string. So of course that is that's sort of in between, and yeah, I mean, this framework in a sense, especially if it's complemented with Matthias and Rajesh's ideas, would be perhaps combined with the integrability would be able to interpolate now. That would be extremely interesting, of course.
So I think we have time for the question of Matthias, although maybe Bo can already stop sharing his screen so that Andrei can start preparing his talk.
I just had a brief question about, so I wasn't quite sure whether you were working in a vector model or in a matrix model. At some stage you had the slides for both. So these calculations were done in a vector model, or?
Yeah, I mean, actually the final result in the extreme high temperature limit, the difference is just in powers of n, how you identify the Newton's constant. So in the results that I displayed, this is the only change between the models. For the lower temperature and lower, larger separations, there will be differences, and that part of those may be in a forthcoming paper. Maybe, though, I think we may focus still on the vector case in those, but it's possible to do the same story for matrices, yes.
Okay, thanks.
And well, since Andrei started to share and try to fix things, maybe then the short question by Mihailo Chubrovich.
Thanks for the nice talk. So I was wondering, as far as I understood, well, the origin of mixing is really that you have the same constituent field phi making up these various operators, and then this perturbation by the compact object. So how much does this really hinge on the system being thermal? If I had something else in the bulk, which is nothing like a black hole at all, and it's nothing thermal, wouldn't I see basically the same picture, still operators mixing because they're made by the same constituent phi and interacting with whatever there is inside?
I think you're right. If you have some background that is non-trivial, if in vacuum it's arranged so that these things will not be seen directly. Sure. But yeah, you could have other interesting background fields. I think so. Yeah, although I have no direct proof of it. Yes, I believe that you're right about that.
Mm-hmm. Thanks.